Okay, so we're going to talk about how we can understand logarithms. And then we've got two parts to this lesson. We've got 1B.1 and 1B.2, which we'll go through the notes together at the start. Bit of a recap of what you've done in the holiday homework. And then we'll move on to 3 and 4, where we start to look at solving equations and natural logs with Euler's number. So we've got basically, I'll teach for two parts this lesson. To start with, we'll talk about how we can understand logarithms, what they mean, and then we'll talk about some skills we're reasonably familiar with. So we're on the page revision of logarithms, and we can see the function there, the graph y equals 10 to the power of x. Okay, and so if you were to graph that, if you have, this is the function 10 to the power of x, and we have, x is 0, then the y value would be 10 to the power of 0. Any number to the power of 0 would be 1. So the first coordinate when x is 0, y is 1. That's the y-intercept. If we have x is 1, then y would be 10 to the power of 1, which is 10. If x is 2, then y is 10 to the power of 2, which is 100. 3, 1,000. 4, 10,000. So you can see exponential growth, right? This is an exponential function. Now, let's point out what we notice here. Notice, log of 10 to the power of x is equal to x. Log of 10 to the power of x is equal to x. So what that means is, we're familiar with this one. If we have log of 100, this is a logarithm in base 10, right? We know it's base 10 because there's no little subscript written here. There's no little font. So this is logarithm in base 10. Now, I'll just be clear as well. For this first part, just have a watch of what's going on up here. Just explain a bit of theory. You don't need to write any of this down. It's all in the notes. And so what that means is we need to express this number as a power of 10. That's 10 squared. Once we have logarithm in base 10 of 10 to the power, it just simplifies to that power. So that's this rule here, right? Log of 10 to the x simplifies to x. So if we put in our calculator then, log of 50, if you type that in, you'll get 1.7. It's like 1.69 or 1.7. Okay? And what that means, okay, what log of 50 means, is it means 10 to the power of 1.7 equals 50. That's what log of 50 means. Okay, if we have log of, I've got another example written there, log of 65, if you put that in your calculator, you get 1.81. What does that mean? It means 10 to the power of 1.81 equals 65. So you can start to see a relationship here. This is what we call a logarithmic statement, because it's a statement about a logarithm. Okay, it's a statement of equality for a logarithm. This is an exponential statement because we have a power, we have an exponent in an equality statement. So that's what logarithms mean. Now I've explained it in base 10 there, but it also exists for, this is the graph of base 2. So we have the same explanation for logarithms in base 2. So just our concluding point there. Therefore, log in base A of m means A to the power of what number will give you m. Okay? That's what logarithms mean. Nonetheless, you don't need to understand what they mean to perform the algebra. So let's flip the page and let's get into the problems that we're familiar with. So, our first one, we have write an equivalent exponential statement for the following. We have log of 100 equals 2. What we're going to do here, this is a logarithmic statement. We need an exponential statement. Okay, what's my base? My base is 10. So 10 to the power of 2 equals 100. That's our answer. We've moved from a logarithmic statement to an exponential statement. Okay? This logarithmic statement has implicit in it this exponential statement. Okay, on to B, we have log in base 3 of 1 on 9 equals minus 2. Alright, so following the same logic, here the base was 10, so we put the base there. Here the base is 3, so we put the base there. 3 to the power of minus 2 is equal to 1 on 9. So just moving from a logarithmic statement to an exponential statement, starting to recognise the relationship there. Okay, so that was question 1. Let's move on to question 2, where we're doing the opposite. We're starting with an exponential statement, and we're going to write an equivalent logarithmic statement. So the first one we have is 10 to the minus 3 equals, now we need an extra 0 there, 1 on top of 1,000. Not 100, 1 on top of 1,000. Okay, so quickly put that extra 0 in. This is the question. So this is an exponential statement, right? You can see pretty similar there. And we want to move from an exponential statement back to a logarithmic statement. So firstly, it's a logarithm in base 10. Now you don't need to put the base 10 there, but you won't be penalised if you do, right? We can put it there to make this extra point, but if it's not written there, we assume base 10. So we have log in base 10 of what? Always of this number. Okay, always of this number. So it's 1 on 1,000. And log in base 10 of 1 on 1,000 will simplify to minus 3. Alright, so I'm putting that number there, I'm putting that number there, and I'm putting that number there. We're just reusing the same numbers, putting them in an alternate order, right? So that's we've moved from exponential to logarithmic. Let's move on to the second one. We have 2 to the 4 equals 16. This time my base is 2, so I have a logarithm in base 2, so that number's going there. The 16 is going here, and it will evaluate to 4. Okay, there we go. So that's just making a connection between logarithmic and exponential statements. Let's go here. Log in base 5 of 5. What we're doing, we have a logarithm in base 5, we want to simplify it. We need to express this number as a single power of 5. Well, 5 by itself is 5 to the power of 1. So the logarithm in base 5 of 5 to the 1 will simplify to 1. We've expressed it as a single power of 5. Okay, log in base 2 of 32. We need to express 32 as a single power of 2. Alright, so we should be pretty comfortable with these. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4, 16. We're getting there. 2 to the 5. We're not just doubling each time, right? 32. So that means 32, we can express that as 2 to the power of 5. Alright, so we have expressed 32 as a power of 2, and so now we will just simplify to the 5. Alright, for C we have log of 1 on 100. So the base here, there's nothing written there, so we assume base 10. So that means I need to express this as a single power of base 10. So we're going to do a few index laws. Firstly, 100 is 1 on top of 10 squared. Now the issue here is that it's at the bottom of the fraction. So we need to take it to the top, and we do that by making the power negative. This becomes 10 to the minus 2. We've expressed this as a single power of 10, which means it simplifies to minus 2. Good. Alright, we've got D. So they'll get more complex. Log in base 3 of the square root of 3 on top of 9. Alright, the base is 3. We need to express this term here as a single power of 3. We need to collect it somehow. So in the first step, the square root of 3, that is the same as 3 to the half, and 9, that is the same as 3 squared. Okay, so I've expressed both the numerator and the denominator in terms of 3. And then I'm going to use index laws. Because they're the same base, I can do the top power, subtract the bottom power. So this will become log in base 3 of 3 to the power of a half take away 2. Okay, the top power take the bottom power. Now, these kind of fraction operations, we want to be really competent at doing manually. I mean, you can rely on your calculator to do something like that if you want to. But I really encourage you to develop competency with these sort of basic fraction operations. So I'm going to go into that in detail. If we have half take away 2, before we can perform this, they must have the same denominator. Here we have a denominator of 2, so we want this to have a denominator of 2. One way we would write that is 4 divided by 2. 4 divided by 2 will give you 2. They now have the same denominator, so we can perform the operation. 1 take away 4 would be minus 3, all on top of 2. And of course that's true. If you have half and you take away 2, you've got minus 1.5, don't you? Minus 1. So the power here will simplify to minus 3 on top of 2. Okay, we've expressed this as a single power of 3. So now it will evaluate to minus 3 on 2. Alright, log in base 5 of 0.2. Now some of these you might need a little bit of prompting to see, but 0.2, that's the same as 1 divided by 5. Okay, 1 divided by 5. And we would express that as 5 to the power of minus 1. So when I have this 5 just sitting here, the power on it in the denominator, that power there is just 1. Any number by itself always has a power of 1. We've got 1 more of it. And so if we're to take it to the top, it makes it 5 to the minus 1. We're moving it from the denominator to the numerator. We have to make the power negative. We've expressed it as a single power of 5, which means it will simplify to minus 1. Okay, we're on to question 4. So in question 4, we're going to be using the rules of logarithms to collect these. And all of the rules that we need to know for this exercise are stated here and they're shaded in. So the first one we have is we have log of A plus log of B. We've got log of 2 plus log of 10. That's going to become log of 2 times 10. Okay, log of A plus log of B is log of AB. Log of 2 plus log of 10 is log of 2 times 10, log of 20. Okay, so that's 4A. I'll do 4B here. All right, we have log of 120, take away log of 6. Now we want to express these as a single logarithm. So this time we're using the second rule listed there. Log of A take B becomes log of A on top of B. 120 divided by 6 will be log of 20. Alright, so if you look, log 2 plus log 10 we saw was log 20, and log 120 take log 6 is log 20. These are the same number, just different ways of representing it. And we say there's infinite ways we can represent any number actually. Okay, we're on to C. Alright, log in base 2 of 5 plus 3. Log in base 2 of 5 plus 3. So we can't combine these just yet. We need to manipulate this. We need to express this as a logarithm in base 2 before we can collect them. And so I'm going to show you what it is and then explain why that's the case. Log in base 2 of 2 to the power of 3 will simplify to 3. Okay, so we're just doing the opposite. We need to express it as a logarithm in base 2 of 2 to the power of 3. Now these are logarithms with the same base. Alright, now 2 to the power of 3, we wrote these up before. 2 to the power of 3 is 2 times 2 times 2, that's 8. Okay, now we can collect them using the first log law. 5 times 8, which is log in base 2 of 40. Now, if this is a skill you need to practice, moving from an integer to a logarithm, that part there, let me know. I can help you out there, but I think we're okay with the rest of the skills. So that's part C. Okay, on to D. I'm so very close to fitting it all. Let's see, I reckon we can. We've got 3 log 2 plus 2 log 3. Now, before we can combine these, we need to get rid of those coefficients out the front. And one of the log laws is, okay, the third log law, if I have n ln a, or n log, I shall say log because we're not touching on natural logarithms yet. If I have n log a, we can write that as log a to the power of n. We can take that number and make it a power. So let's do that to both of these terms. This would be equal to log 2 to the power of 3 plus log 3 to the power of 2. We'll evaluate both of those. 2 to the power of 3 is log of 8. 3 to the power of 2 is 9. And then we'll use the first log law to bring them together, mash them together to one logarithm, 8 times 9. And where are we, year 12 method students? We know our times tables, 72. Okay, last one, question 5. I won't do it there because I want to show you 2 connections. I'm going to do it up here. And there's a couple of connections to point out with this one. I'm always going to be making connections. Connections are important for our comprehension. We have log in base 3 of 9 on top of log in base 3 of 81. And we're just told to simplify it. So I'm going to use 2 strategies. I want to demonstrate 2 strategies for you here. The first is that we can express both of these numbers as powers of 3. Okay? So at the top, boys, I can have log in base 3 of 9. 9 is 3 squared. And at the bottom, I have log in base 3 of 81. 81 is 3 to the power of 4. So it helps to know our 3's as well. 3 to the 1 is 3. 3 squared is 9. 27. 4 is 81. And we probably only expect you to know up to there. 3 to the 5, 243. All right. So we're happy with that. Now, if we just focus on the top, logarithm in base 3 of 3 squared, that just simplifies to 2. So at the top I've got 2, and at the bottom, log in base 3 of 3 to the 4, that just simplifies to 4. So we have 2 on 4, and that's the same as half, isn't it? Okay? The other connection I wanted to make, right, is if we've arrived at this step, okay, one of the third log law we've learned is we can bring this number out the front, okay? We could express this as 2 log 3 of 3, okay? We can bring that power out the front. And the same with this last one. Okay, and why that's useful is because we have the same thing as a product at the top and the bottom, which can cancel. We have log in base 3 of 3 at the top, log in base 3 of 3 at the bottom, it can cancel. We're left with 2 on 4, which is a half. That's an alternative way of doing that one as well. Okay, good. I'm going to stop there. That's enough to do 1B.1 and 1B.2. So we'll spend about half an hour and then we'll have a look at 1B.3 together.
Yeah. How do you do this?
2 times 2 to the half.